Welcome everyone to that webinar about revolutionizing automotive product development with AI-powered engineering featuring Autolive. Let's quickly do some housekeeping. During the session, attendees will be muted. We can have questions and please submit them anytime in the chat box when we then will cover them at the end in the Q&A session. And mind that there are translations available for several listed languages. Let me introduce myself and today's speakers. My name is Moritz Frenzel. I'm a Global Technical Director for Engineering Data Science in the Automotive vertical of Altair. Then I'd like to welcome Srivatsa Yagalur. He's the Global Leader of AI for RDE processes coming from Autolive. And there is Christian Bohnenberger, a Senior Expert in Engineering Data Science from Altair. Let's have a look on today's agenda. I'll start with introducing you to AI-powered engineering from Altair. Then I'll hand over to AI-driven product validation given by Srivatsa Yagalur from Autolive. And then we end that session with a tool demo of Physics AI given by Christian Bohnenberger. At the final end, we'll have a live Q&A session. There has been a paradigm shift from human-assisted computing to the era of intelligent problem-solving with artificial intelligence, and Altair is leading AI-powered engineering evolution. Let's focus today on AI-powered design, but keep in mind that AI-powered engineering and AI-powered manufacturing are also valuable parts with software support from Altair. Let's look on this, to me, very appealing animation of a simulation result. On the left side, it's the simulation result of one Radius advanced simulation, taking into account multi-physical effects and representing the contact pressure of an airbag hit by an impactor. On the right side, you see that same animation, but not represented from a solver result, but represented from an AI model, a physics AI model, being trained on roughly 50 samples of such simulations, but which gives you predictions of any of these cases within 30 seconds instead of 2 hours it'll take for one further simulation based on our structural solver Radius. This work has been worked in collaboration with Continental, and it shows the sheer time saving you could gain with upfront training of AI models and then leveraging them into your design phase. So that's why AI-powered engineering speeds up development and innovation, and where maybe in the past or still today, a test may take a week, a simulation may also even take some time and represent a bottleneck in the design processes where some would like to have prediction in seconds. For that same airbag case, on the left, you see a video of a real-time test, which is already something quite advanced and sophisticated in engineering. In the middle, you see the animation of result of such a simulation. And on the right side, we just sketched here the sheer amount of maybe 50 or hundreds or even 500s of these airbag simulations. It's impact to variance animated on the right side of things, which could be a base data set for a trained AI model to be relevant and supportive within seconds. But airbags and in general passive safety are crucial, carefully designed physical assets which represent trust in traffic since decades. We will learn about this later from Autolive. So a black box AI would be prohibitive, but AI as tool in the hands of engineers is enabling faster development, coping with complex physics and vast data sets. And that's where software solutions from Altair are ready for deployment. Let me introduce you the CRISP-DM process, the cross-industry standard process for data mining. You can find this on Wikipedia, and it's been introduced in the late 90s, breaking down a successful data project into 6 major phases. It starts with business understanding, then goes to data understanding, data preparation and modeling, and comes evaluation and deployment. And that circles around data, and the circling of this process is important and should be not underestimated to follow around this. For simulation, that can be historical data. It could also be design of experiment data, whatever is at your hand. Then training a physics AI model to result in what I've shown before will be demoed in the third part of that webinar. But in short, it could be run locally or on the cloud. And the validation element is right where CAE people validate their simulation results as well. So you can show your contours, you can cut through models just the same as it would be a simulation result, making sure that your model has the appropriate accuracy. I'll come to accuracy in a minute, but let's start the circle where it really starts. It starts with business understanding. And being on the market for simulation-driven design for decades, we from Altair, we know the business of CAE design engineers and how they work with their data, and how they interact. Now, a very important and sometimes underestimated phase for successful and highly accurate and productive models are data understanding and data preparation. In simulation, we have to deal with large, complicated data sets per sample. And this is where we from Altair serve an essential part to create support you in these processes with our tools. Examples of data curation are add, remove data points, rotate things, convert, filter, down select, and on the overall data set, check your bias and eventually have an outlier detection process. Clustering is actually a very basic but also very powerful method to support this data curation and outlier detection, for instance. So let me zoom in what that would mean working directly on simulation results. We have the example of belt submarining for dummies. Experts of you know this process, but I think also engineers understand that the belts of a car seat should hit the right position of these dummies, and submarining would mean that the dummy actually dives under the belts. This is a very expert-driven problem, and working on labeling submarining yes or no normally would take very detailed analysis of, for instance, angles or individual accelerations, where if you could work on the whole simulation results for, let's say, 50 simulations altogether, that clustering is a very intuitive way to, for instance, here, separate 4 clusters, where cluster 4 seems to be obviously non-submarining. Cluster 3, several simulation results represent that not wanted case of submarining. Cluster 2 represents non-submarining again, where cluster 1 has some submarining or might be a little bit vague, but that way of separating your data set is very intuitive, and you can label this whole data set in minutes without or with at least very little domain expertise by just using the whole simulation result data. Let's go one step further and look on data curation for thousands of external error simulations. Here, you really need to understand the geometry variation included in your data. You need to understand the result distribution, identify hotspot distributions, and all that kind of things. And obviously understand the KPI range distribution of your data. All this is very important if you want to have this amount of data brought into a really accurate AI prediction model. Now let's continue for the modeling aspect, where I've shown physics AI as one element. Another element could be a ROM AI, which would be a reduced order model, and that could be trained with Altair's ROM AI product, which is then suited for system level applications. Continuing on that circle, it comes to deployment. And deployment, maybe together with evaluation, has been shown right in HyperWorks. So at the hand of CAE people who understand how they would evaluate a simulation result, but now can check a potential deployment of a physics AI model and thereby explore in real time their data set they have brought into modeling. But let's think about other options to deployment. Fast and performant AI models could be integrated in simple or even quite advanced optimization loops, which is the way towards generative design, or rather in a collaborative environment. AI models could be governed by someone understanding the whole process of generating and training a model, but then consumed by others like design engineers. Let me show you how such a dedicated dashboard solution could look like. That's a Panopticon, which is a product from Altair, dedicated dashboard consisting of several elements, including a physics AI pre-trained model, which is then run for new geometries coming from a CAD designer, maybe together with other informative data and based on the relevant input data. So such deployment options could be really speeding up or democratizing the leverage and the usage of AI predictions. Or the real next thing, or if you want to think big, then we offer Physics AI Studio as cloud solution in Altair One, which would bring prediction and consuming models right where your data sits, which would be, at least in future, in the cloud. So summarizing that whole circle, it is important to follow it for really accurate and valuable AI models, returning your investment and speeding up your development. And Altair products and solutions serve you all the way around that circle. I've shown it basically on an example of an airbag. However, our solutions are physics agnostic. That means that simulations from, well, durability or fluid or thermal or electromagnetics are all very well suited to be brought into such advanced AI prediction processes. With this, I'd like to conclude my introduction and want to hand over to Srivatsa Yagalur, representing Auto Live, on their AI journey to AI-driven product validation. Srivatsa, over to you.
Hello everyone. Thank you for joining this webinar. I am sure all of you have enjoyed Saving More Lives video. Let me introduce you to Auto Live as the worldwide leader in automotive safety systems. We develop, manufacture and market occupant safety systems such as airbags, seat belts and steering wheels for all major automotive manufacturers in the world, as well as mobility and safety solutions. At Autoliv, we challenge and redefine the standards of mobility safety to deliver leading solutions sustainably. In 2023, our products saved 35,000 lives and reduced 450,000 injuries. Our 70,000 colleagues in 25 different countries are passionate about our vision of saving more lives, and quality is at the heart of everything what we do at Autoliv. We drive innovation, research and development at our 14 technical centers with their 20 test tracks. With the vision of saving more lives, our mission is to provide world-class life-saving solutions for mobility and society. Our key behaviors express the essence of our ways of working in a clear and consistent way and define how we strive to achieve success together with colleagues, customers, and also with our partners. You have already heard from Dr. Moritz about how AI-powered engineering is transforming the engineering landscape. Let us look at what is happening in the evolving field of scientific machine learning, what we call a new era of solver technology. If we look at our history, we know how the simulation gained its importance in new product development while contributing to reducing the physical testing. In a similar way, the scientific machine learning is evolving too and leading us to data-driven product development. Integrating physics prior to machine learning model has had a significant impact on the literature in scientific applications. The number of papers referring RIAC and others are including physics-informed neural networks in their abstract title or keywords is increasing exponentially. From the solution to the 1D nonlinear Schrodinger problem through physics-informed neural networks in 2018 and 2021, the researchers coupled successfully the Navier-Stokes equations with the corresponding temperature equations for analyzing heat flow convection in the physics-informed neural network framework. This continued to evolve into many different versions of physics-informed neural networks, and today we see many research topics on physics, multi-physics problems at different scales are being addressed by physics-informed neural networks. The figure shown here is from a paper by Karniadakis and others that schematically illustrates three possible categories of physical problems associated with the availability of data. In the small data regime, it is assumed that one knows all the physics and the data provided with that. And there is a regime with big data where one may not know any of the physics and where a data-driven approach may be the most effective. For example, using operator regression methods to discover new physics. The ubiquitous regime in the applications is in the middle one, where one knows some data and some physics. Most of the challenges in today's industry for product development lie in this regime. Physics-informed machine learning can seamlessly integrate data and governing physics laws, including models with partially missing physics in a unified way. Autoliv's mission is to empower our engineering teams with AI tools to automate routine tasks, enhance predictive accuracy, and streamline data analysis. Our main focus areas are shown here, which is leading us from short-term gains to achieve our long-term goals. Performance prediction by AI is one way in which we are focusing using our historical data to build machine learning models that can be used in our design validation processes. But this may not be sufficient to address the data sufficiency challenges. Hence, we have other focus areas like data quality enhancement, wherein we are trying to unify our historical data complementing to our historical test data, complementing to our simulation data to build a robust predictive models. Furthermore, the roadmap is also to scale the using GenAI algorithms to quickly help in exploring the design space. Here is one such example of validating steering wheel armature for structural load cases. As this product must satisfy multiple objectives in parallel, including multiple CE solvers. And herein, I'm showing the static and dynamic load cases with the target results which we have to satisfy to validate the design of steering wheel armature. When it comes to data, when I say accumulated knowledge, what it means, we already have historical simulation data, which can provide us insights on the behavior of different design variants across different programs. But the most challenging part is here is the revalidating any minor changes in the design updation would take good amount of time to run or rerun the simulation again. This would impact the delay in our design decisions as well. Requirements from OEM are very diversified today based on the customer demands and competition scenarios. This is just to give a glimpse on how complex the different shapes, the number of spokes, the material combinations, these all play a vital role in deciding the selection of steering wheel for different variants of vehicles. Now, this is where the crucial things come for us to have a lead time reduction in our entire product development cycle to contribute to the OEM demands. As we already saw that how the scientific machine learning are evolving and data-driven product decisions are becoming more evident, and it is quite important to embrace this technology to reap early benefits. With a brief introduction that already Dr. Moritz spoke on engineering data science, we really saw using physics AI as a part of the process was very seamless if you wanted to train your historical simulation data and use it for predictions over CAD and FEMesh or finite element models. We have seen significant accelerations when the data sets are trained using GPU clusters. We were very cautious about using hyperparameters of the deep learning architecture in training the models here in both the use of both use cases, which I talked about in the previous slides. I'd probably say we started training huge data sets with the default hyperparameter. Understanding the loss curves and the confidence scores, we started fine-tuning them like solving any other non-convergence results. Also had to look back at the data set if we had to identify any outliers. The confidence scores were pretty much in our acceptance range, coming close to 90% of accuracy of the prediction. Wherever we observed the confidence score was not meeting the criteria, we looked at sensitive parameters, including increasing the size of the data sets and also the variance in the data itself. One of the features that we used in our program for dynamic load cases was the creation of custom hooks like JSON using Python scripts in extracting the deceleration plots for the dynamic load cases. What are we doing by embracing this technology? Aligning to the organized goals of short-term to long-term gains, we are reinventing the design process and democratizing the AI augmentation between CA designers and to reduce the lead time reduction involved in the new product development process. Here in this slide, you can all clearly see the paradigm shift that we are focusing on bringing from CA-driven decision making to AI-augmented decision making by involving the design engineers at an early stage of design validation. Since physics AI can run in batch mode, we are further exploring options of bringing a neutral dashboard for interaction between CA and design teams, which could be a hybrid solution as well. With this, I conclude my presentation, and I thank Altair team for this opportunity. And now I hand it over to Dr. Moritz back for the next presentation. Thank you, everyone.
Thank you, Srivatsa, for this intriguing show how Auto Live drives their transformation. Now we want to come to the demonstration of the tool Physics AI given by Christian Bohnenberger, who actually shows it based on a collaboration with Magna Cosma, where Istvan Soproni from Magna Cosma says that Altair Physics AI enables them real-time feedback for design changes of their crash management systems. Christian, over to you.
Hi, my name is Christian Bohnenberger. I'm a senior expert for Altair Physics AI, and today I show you the workflow how to train a Physics AI model in the Altair HyperMesh tool environment. For that, I brought with me an example from the crash safety domain. It's about the prediction of the folding behavior of a crash box. Crash boxes are widely known in the automotive industry for their complex development cycle, their sensitivity against small design changes, and their long solver runs to evaluate with a structural solver. Crash boxes are highly nonlinear, and they are solved in a transient way. To accelerate the development cycle, Physics AI can predict the behavior of the crash box instead of a structural solver. To train a Physics AI model, data is needed. We have 147 samples for this crash box, and their variance is in geometry, in shell thickness, and we have some material parameters. It is important to know what kind of designs you have in your model, and it's also important to know what kind of results you expect from Physics AI. In this case, we are looking at the distribution of the strain and the deformation patterns. With that being said, we go in the HyperMesh environment, and I show you how the training of a Physics AI model works, how to test the trained model with unseen data, and how to use a trained model for prediction of new designs. To use Physics AI in HyperMesh, we add the Physics AI ribbon. To start a new training, we create or open a Physics AI project. After we open the project, we can create a new data set. In this case, a training data set with 135 samples out of the 147 samples is already created. To show you how to add a new data set, I extract the 12 missing testing samples. To do so, I click on the plus button, select a path to my data, and add the found result files to the right side. I provide a name and click OK. While this is running, let me show you how the directory structure is. So every folder has I have a 3D files as result files. And additionally, I have two separate files that include the thickness data and the material properties. We use a functionality, it's called custom features, to find these files and add them to the dataset. When the dataset is extracted, we can check the data we have here. First of all, we can check Also, we can check displacement and plastic strain, so we know these are the result types we have in our data. We can see, in this case, the maximum values per model or the mean values, whatever we like to see here. If we want to check the data specifically, we can display the file in Hyperview. The result file gets imported, and we can see if there's anything, if there's anything with the model. If we're satisfied with the imported data set, we can go to the next step, model training. To do so, we go back to the HyperMesh window and go to the model training button. The step is to create a model. First, we provide a name. We select the training data, in this case, the 135 training samples. And then we select the input features. We need the coordinates for the geometry, and we need the material and the thickness data that we provided with the custom features to the data set. Then on the right side, we select the outputs. We can select all the outputs we like. In this case, we use displacement and effective plastic strain. On the bottom, we can now select the architecture we want to train with. For this crashbox, we use the new Transformer Neural Simulator. On the right side, there are some hyperparameters we can adjust to fine-tune our model training. For now, we leave it as default. If we're done with the settings, we hit train and wait for the training to start and then for the training to converge. While the training is running, we can show the log file to see the progress of the training. We can also check the loss curve after it's done. So the first step is to extract the features and build the labels. This takes a few minutes. Now we need to wait until the model is converged. To accelerate the progress in here for this demonstration, I'll stop the training and import an already done training. For that, I click Import Model, go to the location where my model is, provide a name, and import the model. When we have imported the model or the model is fully trained, we can go to the next step. It's the testing and validation step for physics AI models. For that, we open the model testing window. We click on Test Model. We select the model we like to test, and we select the testing dataset. We hit OK and wait for a second that all the models are predicted in the background and evaluated against their simulation reference. When the model testing is done, we see some error metrics on the screen. First of all, we see the overall error. So it's the absolute difference between the prediction and the simulated reference. And that we see for the plastic strain and for the displacement. Down here, we see the error metrics for every file, for every sample individually. And if we would like to have more information about error metrics, we can click on the detail report to see, for example, the error metrics for every time step. If we want to have a direct comparison between predicted and true, we can click on the Display File button to see on top the prediction and on the bottom the simulated reference. Now, as we are in Hyperview, we can have all the post-processing capabilities we can do with simulated results. We can do them as well in the simulation as in the prediction. When we are overall satisfied with the performance and the accuracy of our model, we can use this model for prediction purposes. For prediction purposes, I import a new design file from my data. In this case, it is a key file. I import it, and I can see this geometry. So this is a new design that we need to predict on. To do so, we click on the model training, and we set the trained model as active. And the last step is just to click on the predict button. And in the background, the model is predicted. And in a few seconds, we'll see it on the right side in a Hyperview window. As you can see, the model is predicted on the right side. And we can animate it. So we trained all the time steps we have in our training samples. Not only can we display now the displacement, but as we trained plastic strains as well, we can switch the contour to the plastic strain approach. So you can see it is fairly simple to use a trained model and predict right away the results. So with that, I'm at the end of my presentation, of my demonstration. Thank you for your attention.
Thank you, Christian. Now let's come to the Q&A session. We're happy to answer your questions. Thank you very much. Goodbye.